So in this unit, we have discussed so far linear functions as well as the use of x and y intercepts in order to graph the line, identify the points at which the x value is 0 for y-intercepts, and the points at which the y value is 0 for x-intercepts. What we're going to be discussing today is the idea of rate of change and slope as a tool within linear functions. So the first thing that I would like for you to consider is the idea of rate of change. We know, for example, that if you are traveling at a rate of 50 miles per hour, let's say, what this is representing is 50 miles being traveled in 1 hour. We understand the idea of rate as a comparison of two different units, such as miles and hours. And if we were to track the change in our speed, we could write it in a table of values such as this, where let's say that the distance traveled depends on the number of hours that you're driving. So if we were going to identify the dependent and independent variables based on the knowledge that we've already gathered, we know that if the distance depends on hours, then the distance is the y and the hours is the x, because the y always depends on x. So if we were to put the variables up here on the rate, we would symbolize that miles is the y and that the hours is the x. So if I was to track 50 miles in 1 hour, then if I am traveling at the same rate, 100 miles would be completed in 2 hours. 150 miles would be completed in 3 hours. And if I wanted to say that I traveled, let's say, 200 miles, and it actually took me 4 hours, we would want to see if we are traveling at the same rate by looking to see the number of hours changed was 1 from here to here. From 2 to 3, I went up by 1. From 3 to 4, I went up by 1. I went up by 50 here. I went up by 50 here. I went up by 50 here. So I know that I am being consistent in my rate. That is a constant rate that I am changing at. If I was to create another table of values and I was to say something on the lines of, I'm traveling 50 miles in 1 hour, and I travel 60 miles after 2 hours, and I traveled 200 miles after 3 hours, you can notice that this is not the same rate of change. I traveled 10 miles here, and I actually traveled an additional 140 miles, while my hours increased by 1 here and increased by 1 here. So there is no consistency in this, so this would not be a constant rate. So if we're going to talk about the language of rate of change, we can see that the rate of change tells us on average how a quantity is changing over time. It's a ratio that compares the amount of change in a dependent variable to the amount of change in an independent variable. So dependent we know is y, and independent we know is x. The rate of change is symbolized by writing it as a fraction, where the numerator discusses the change in y that occurred, the amount that changed for the dependent variable for every change of the independent variable. So let's take a look at an example here. It says the table of the right shows the balance of a bank on different days of the month. It wants us to find the rate of change for each time interval, and then it wants to know during which time interval did the balance decrease at the greatest rate. In order to do this, we are going to look at the two different variables. We're going to look at the dependent and the independent variable, the x and the y. If we look at the change of y, we notice, that From 550, I went down to 285. That change was 265. It was a 265 decrease. The amount of days went up by 5. So for this time interval, the rate of change, which we use the Greek letter delta to represent the word change, the rate of change for this time interval would be negative 265 over 5, which gives you a value of negative 53. So the rate of change for the first interval was negative $53. So interval number 1, we're going to call this interval 1. You lost $53 in 1 day. It's per day. We simplified that. The next interval, from 285 to 210, you lost $75. And this was an increase of 10 days. So the rate of change would be negative $75 for 10 days. So how much was that per day? Negative 7.5. That means that interval number 2, you lost $7.50 per day. Interval number 3, I went from 210 to 210. So that was a change of 0. And yet, there were 6 days that changed. So this is going to be 0 over 6 and anything. 0 divided by 6 is 0. 0 divided by anything is 0. You can't take 0 and divide it by 6 people. Each person would just get 0. So the second or the third interval, you lost $0 per day. The last interval, I actually lost $35 in a span of 8 days that increased or had passed. So this interval would be negative 35 in 8 days. When I divide that to figure out how much it is per day, 35 divided by 8 gives you about 4.375. And we're talking in terms of money, so we always round to the nearest penny. 7 looks at 5, and 7 becomes 8. So the fourth interval changed by dropping $4.38 per day. So during which time interval did the balance decrease at the greatest rate? It was during the first time interval. So the first 5 days were the group, the first interval, that I lost the most. If I was to graph this data on my chart, I would refer back to the table, and I would know that at day 1 I was at 550. So I'm going to go to day 1, which is probably right about here, and I was at 550, which is probably right around here. Day 6, Day 6 I was at $285. So day 6, 285 would be somewhere around here. The next day 16, I was at 210. So day 16 is right about here. 210 is below the 225, which would be right about here, let's say. Day 22 was at 210. So that's going to remain the same. It's going to be day 22 is literally right at the same place. And then the last day which we recorded, which was day 30, was at 175. So day 30, 175 is just below the 180 mark. Now, if we were to connect these dots as linear as we can, and it's difficult to make a straight line without a ruler, and then we would show the rates of change, we can see that at this point here, this section was the first rate of change, which was losing $53 per day. this rate of change that occurred was the second one, which was losing $7.50 per day. This little section right here that did not change, and it should be a completely flat line, is $0 per day. And this last section right here was we lost $4.38 per day. So you could see that if we were to look at this function itself, this is not linear because of the fact that it is not constant. There is no constant rate of change. If there was a constant rate of change, then it would be one full perfect line. So this is not a linear function, and the rates of change are not consistent. They're not constant. Our next example that we could talk about with rate of change is this one here. We're looking at the graph. This graph is showing the density of population for the state of Ohio from the year 1920 to about 2020. Their predicted amount obviously is not here. We're not at 2020 yet. But we do have data up till the year 2000. They ask us to find the rates of change between 1930 to 1960 and then between 1990 and 2000. So remember that rate of change, as we just discussed, is the change of y over the change of x. It is a rate, and so it is always written as a fraction so that you could see the change of the y, the dependent variable, over the time of the x. From 1930, which was 5.4, to 1960, which was 8.1, the change that occurred is the difference between the two, obviously, because when you're calculating how much change occurred, you're subtracting the two variables or the two quantities, and you want to know how much actually physically changed. When we do this math, we discover that this gives us a negative 2.7 change. The change of x is the years. We went from 1930 to 1960, which is 30-year span. So the rate of change, we went from 1930 to 1960, that's negative 30, because we're subtracting 1930 and 1960, even though 30 years passed. If you take 1930 minus 1960 physically as a number, they're integers, and you would get negative. So once we get the calculation of that, once we do our division, and you can use your calculator for this, you get the value of 0.09. This here is a 9% change. That's a percent symbol. I know sometimes 9% change in population. The next interval that they asked us to complete the rate of change for was from 1990, which is this one, because this one says 1980. So from 1990 to 2000, which is this one. So the change of my y is from 12.2 minus 15.6, and the change of x is from 1990 to 2000. Doing the mathematics, we get negative 3.4 over negative 10, which, once you do the division, well, anything divided by 10, you're literally just moving the decimal one to the left. So this is really 0.34, 0.34 or 0.34, however you want to see it, which is a 34% change in population. So we see that in real-world applications, we can actually use rate of change to figure out how much something is changing within a given amount of time. For the first interval, we know we went up, so this is a 9% increase, as well as for the 12.2 to 15.6, we also went up. So that is also an increase in population. What they would like for us to do now is to explain the meaning of rate of change in each case. That was basically what we explained. That was that for the 1930 to 1960, there was a 9% increase in people per square mile. Because if you recall, we look here and it says people per square mile. And then with the other rate of change between 1990 to 2000, there was a 34% increase in people per square mile. Looking at the graph, if we were to connect the dots to show visually the change that occurred, we would notice that there was a rise here, as well as here, a little one here, and then a much drastic one there. So you see that the actual rate of change is kind of like different between each section. Which leads us to now discuss the actual algebraic application of rate of change. The word slope is actually synonymous with rate of change. So whenever you see the word rate of change or changing at a rate of, any of those words, it's basically telling you it's the same slope. Just like we talked about how the steepness changed over time in different parts of intervals of the data that we looked at in the graphs, you could see that the rate of change is the same thing as slope. The slope of a line, as we kind of talked about also in pre-algebra, is the rise over the run. It's the change of y over the change of x. To rise, you are going up vertically on the y-axis. To run, you are running from left to right. You're going to the right. It's how far you go over on the x-axis. And so if we're looking for the change, it's really the difference between the two values of the y over the difference of the two values of the x. There are 4 types of slope that you can have of a line. Going from left to right. If you are going up, it is a positive slope. Going from left to right, if it's going down, it's negative. If it's gotten a flat line, it has 0 slope. And an undefined slope is a vertical line. A couple of ways to figure that the difference between the two. If you think about the idea of rise over run as slope, we know that the change of y, or the rise, over the change of x, which is the run, if we have a fraction, if I don't change anything on the y, and I change, I don't know, any value, you remember that 0 divided by anything will always give you 0. If you're going to take $0 and you're going to divide them by 5 people, each person is going to get 0 because 0 is an actual value. It's a number. On the other hand, if you were to compare a change of y of 5 units and divide it by a change of x of 0, you can't take $5, let's say, and divide it by 0 people. It's not possible. When your denominator is 0, that is what we considered an undefined slope. So it's basically any number divided by 0 will always give you undefined value. And the reason it's undefined, you can't define it. If you look at the example of 0 divided by x, if I was to take 0 divided by 5, if I was to say something like 10 divided by 5, we know that gives me 2 because 5 times 2 is equal to 10. If I had the 0 example, 0 divided by 5 is also equal to 0 because 5 times 0 is equal to 0. as opposed to the bottom one here. You look at this one. If I have 5 divided by 0, that is not going to give me anything because 0 times any number will never be able to give me the value of 5. That's the reason why it's called undefined. There's another little saying that I like to use just to remind you of the vertical lines giving you undefined slope and the fact that the flat lines, horizontal lines, give you a slope of 0. And that is the acronym VUX HOI, where V stands for vertical, as in vertical lines. Vertical lines have undefined slopes, and they are x equal to equations. They cross the x-axis. See this vertical line here? Right here, if you didn't see that visual with the blue, is crossing the x-axis. The other one, horizontal lines, have a slope of 0, and they are y equals. They cross the y-axis. So here's the horizontal line. Regardless of where it is, if you're a horizontal line on the coordinate plane, you're going to cross the y-axis. So VUX HOI is another way of remembering that vertical lines, undefined, horizontal, slope of 0. Then we also have this little tiny slope dude. A picture that you can think of. If I have a line going up, I am positive. If I have a line going down, I am negative. If I have a vertical line, I am an undefined slope, and a flat line has a slope of 0. So if this kind of helps you, this little cute little face, then you can also use that. So now let's put it to use. Find the slope of a line that passes through each pair of points and then state whether it is positive or negative, or if it's flat or 0. So let's look at this. First of all, we're going to plot our points. We can plot -1, 1, remembering that coordinate pairs are always ordered as x, y. If you plot the 2 points, -1, 1, and you plot 2, 2, you connect the dots, and remember that these are just representative of a section that goes on forever. Now, you could figure out the rise over run by literally going from leftmost point to the rightmost point. You are going to figure out how much the rise was, and I went up by 1. So the rise was 1. And I ran from the point here to the point here, 1, 2, 3 to the right, so that's also positive. So that means that my slope for this line is 1/3. And remember, we keep it as a fraction because we want to make sure that we can see the numerator symbolizing the rise and the denominator symbolizing the run. Remember, when you go up, it's positive. You always want to run to the right just to make sure that you don't get any confusing negatives in there. For the next line, again, 1, 3, and 4, 1. We're going to plot 1, 3, which is right here. X of 4, y of 1 is right here. Connect those dots. Remember, you always want to draw arrowheads. Always draw your arrowheads. You're not a line segment. You are a line. You are going through forever. The slope, once more, rise over run. Always start with your leftmost point. The rise could be positive or negative. Leftmost point is this one. From this point, which is at the value of 3, to this point, which is at the value of 1, I went down 1, 2. So my rise is -2. My run, I always want to run to the right because I'm going from left to right. So the run, you went from the leftmost point, which is at 1, to the rightmost point, which is at 4. And when I say leftmost, rightmost, up, like highest or lowest, I'm referring to the points that you can see because you have an infinite number of points here. These are the ones that have been identified for us to use. So the run, I went over 1, 2, 3. And when you go to the right, it's always positive. So the slope of this line is negative 2/3. Just by looking at it, I know it's a negative slope, but it justifies the fact that I got a negative number. So if you're going from left to right and you know it's going to be negative, you need to make sure that if you ended up with a positive, you look to see what you did that might have given you the wrong, incorrect calculation. Okay, let's look at the next one. -3, 6. So I'm going to go -3, which is right here, up to 6, and 4, 6, 4, 6. Now, I connect my dots, and you notice that it's a horizontal line. You remember, hopefully, Vux Hoi. Hoi is HO, 0, or a horizontal line has a slope of 0. So this is horizontal because it's going from left to right, like a horizon. So the slope is equal to 0. Looking at the points, you might even be able to recognize that if you're going to be going up to the same value, 6, that means you're crossing the y-axis at 6. So that means you are horizontal. All right, find the slope of a line that passes through each pair of points, then state whether it is 0 or undefined. Again, you might be able to look at it and recognize this point is going to 2 on the y-axis. This one is going to 2 on the y-axis. Both of the y's are the same, so that means you cross the y-axis, which means you're horizontal. But if you didn't see it right away, that's okay. You just graph the points. -1, 2, and 3, 2. It's a horizontal line. Therefore, it's a slope of 0. The next one, you might be able to look at it and recognize, oh, look, the x repeats itself. If the x repeats itself, that means it's not a function. And if it's not a function, it's because of the vertical line test. So you could either see it just by looking at it, or you graph it, 3, 4, and 3, -2, and you connect those dots and you realize it's a vertical line. And vertical line, Vux, is undefined slope because it crosses the x-axis, as you can see right here. It's crossing the x-axis. All right. What you are going to work on now is the independent practice. Make sure that you go through this, complete it, and we will go over some of these in class tomorrow.